Most high school calculus courses start by defining the derivative, and most high school students wonder why they would ever need to know what a derivative is when that happens. And the answer is that a derivative can be broadly thought of as a rate, and that rates appear everywhere in our day-to-day lives. To give you a physical example, if you walked a distance of 10 meters in 10 minutes, you might notice that you walked 1 meter every minute. That rate is a derivative. Generally, speed is the derivative of position. If you later notice that your speed increased from 1 meter per minute to 5 meter per minute over 20 minutes, that rate is also a derivative. So acceleration is the derivative of speed, which is the derivative of position. And rates don't just have to do with time or distance, though. The amount of light a light bulb gives per volt of electricity passed through it, the amount of water flowing into a lake, the rate of interest on your bank account, those are all rates that can be modeled by derivatives. In order to understand why this is actually useful in the real world, you need to understand something called the integral. One not particularly mathematically valid, but still helpful way to think of an integral is that is the inverse operation of differentiation. Just like how whenever you see multiplication in an equation, you divide to find the variable. Whenever you see derivatives in equations, you integrate. The fact that differentiation has an inverse operation allows us to write equations involving the rates we were just talking about, and comparing them with the derivatives of other quantities. Those equations are called differential equations, and they're used everywhere. To give one example, if you were designing a building, you'd want to make sure it didn't fall over. The amount that building sways in the wind can be modeled using a differential equation. When you solve that differential equation, you will know how to design your building so it doesn't sway too far. The equation that describes this behavior is why we can keep building bigger and bigger skyscrapers, and it's why the CN Tower, the Eiffel Tower, and the Space Needle all have vaguely the same shape. It's all because of the Humboldt derivative.